So it's a pleasure to be here. As was mentioned, I'm a security developer at CoreOS. And one of the driving goals behind our work at CoreOS is to improve the security of as much of the internet as possible. And that is a central part of our design philosophy behind all the components that we're working on. So, for instance, as Brandon discussed this morning, one of the driving aspects behind the design of Rocket was the integration of security and making sure that we had images that were signed. So you had confidence that the images that you were running, the container images that you were downloading, were the container images that you expected to be executing, that nobody had been able to tamper with them. But when we talk about having a secure container runtime, the security of that runtime, regardless of how good it is at verifying signatures on images, is only as good as the security of the components underneath it. Sorry, I'm going to apologize for the fact that my slide text is black in an ugly manner. We've had minor technical difficulties, and this isn't my laptop, but never mind. If the security of the underlying system is compromised in any way, you cannot build a secure ecosystem on top of that. There is no way for you to trust that your container runtime is able to validate the images it's executing if the container runtime is itself on top of an untrusted environment. If your operating system is not trustworthy, you have no idea that the container runtime binary you're executing is the correct binary. Even if it is the correct binary, you have no confidence that the kernel is not modifying it in flight, or that the kernel is not modifying the signing keys that the runtime is validating images against. Even if you have a mechanism to validate the kernel, you have no mechanism to verify that the firmware that the kernel is running on has not been tampered with. When we're talking about being able to verify the security of images, we really need to go further than that and make sure that we can verify the security of the system that the containers are running on top of. The obvious question is, how do we trust that? Things like UEFI Secure Boot make this possible in certain respects. A secure boot system will perform cryptographic validation of the operating system components as they're launched, which means that it's possible to say, well, since this system booted correctly, it must be the case that nobody tampers with the kernel, because otherwise the system would have refused to execute the kernel. That's unfortunately not quite good enough, because if the firmware itself has been tampered with, and we've seen that malicious actors are becoming more and more versatile in this respect, more and more aggressive, and we are beginning to see attacks against system firmware, then the firmware can be modified in such a way that the secure boot guarantees no longer apply, and the system is once more in an untrusted state. So we need to go further than that. We need to come up with a mechanism which allows us to not only verify the higher levels of the system, but also the low levels. And we also need a mechanism to prove that this is the case, that a system is in a trusted state. We can't merely assume that it is because it booted. We need a mechanism to verify that at a later point. And the technology around this is called trusted computing. Trusted computing has been around since the early 2000s. It refers to a series of technologies developed by the Trusted Computing Group. When these technologies first appeared, we were concerned that they would be used to restrict the use of systems, that trusted computing would mean that people were no longer able to use the operating systems they wanted, would no longer be able to access websites unless they were running software that had been validated by the website owner. And while these concerns were legitimate, they haven't, for the most part, ended up being real-world scenarios. We have not ended up in a situation where the trusted computing technologies have been used to restrict users. But at the same time, we haven't really seen trusted computing used in any way that enables security either. In recent years, Microsoft have started making use of certain trusted computing technologies in order to enhance the quality of disk encryption on laptops and desktops, and some vendors, some enterprise companies will use TPMs in order to provide VPN credentials. But for the most part, we haven't seen these technologies be widely deployed outside fairly specialized use cases. And we want to start changing this. The basis of trusted computing technologies in the hardware is a device called a trusted platform module. A trusted platform module is a small chip which has very limited capabilities. It's able to perform certain cryptographic operations. It's able to sign data. It's able to encrypt data. But it does this very, very slowly. TPMs are not cryptographic accelerators. If there's any way you can do cryptographic operations on the CPU instead of on the TPM, it's better for you to do that. But what's interesting about the TPM is that it has control over the keys it's using. If you ask a TPM to generate a key, you can ask it to do so in such a way that that encryption key or that signing key will never be released by the TPM. Only the TPM has access to that key. And TPMs are intended to be designed such that even if you have physical access to the TPM, it is still very difficult for you to extract the key from the TPM. One of those keys is called the endorsement key, and the endorsement key is burned into the TPM at manufacturing time. The endorsement key is unique per TPM. Every TPM is intended to have a different unique endorsement key. And that means that we have a unique per system identification. There's no way that another system can pretend to be this system without access to the same endorsement key. And as I mentioned, the idea is that the TPM will never give access to that endorsement key to another system. But the other thing that the TPM does in an interesting way is allow us to verify system state. During the boot process, as the system is being brought up, each component of the boot process can be cryptographically hashed, and that hash pushed into the TPM. And that means that when you turn on the system, the CPU hashes the first block of firmware into the TPM. The first block of firmware hashes the rest of firmware into the TPM. The firmware hashes the bootloader hashes the kernel, and eventually we get to a booted system. And the TPM has control of those hashes. The problem is we can't simply just ask the TPM for those hashes, because if the kernel has been tampered with, the kernel could simply feed us the values we expected to get rather than the values that were actually in the TPM. So the TPM is able to sign those hashes and provide a signed copy of those hashes to a remote system on request. And this is a process called attestation. And this means that we can end up with a cryptographically verifiable copy of the state of the booted system. So because we have these hashes of the boot process, and we have the unique per system key, and we have the TPM's ability to hand that off to another system, we can then verify that these hashes came from the TPM by validating the signature, and we can then verify what the system booted. So we can make sure that the kernel hash matches the kernel that we expected the system to boot. We can make sure that the bootloader hash matches that. We can make sure that the firmware hash matches the firmware that was previously installed on the system. If an attacker modifies the firmware hash will no longer match. The only way they'd be able to compromise this is to be able to actually execute code on the CPU before the CPU started doing anything else. And that's sufficiently implausible that it's an attack model that we can basically discount, unless your adversary is the NSA. And if your adversary is the NSA, you're probably going to have a bad time. But we're not really here just to talk about these things in an abstract manner. And we are at KubeCon. There is presumably some interest in how this fits into Kubernetes. So the rest of the presentation, I'm going to be not so much focusing on the underlying technology and more talking about how we can fit this into Kubernetes, not only to enhance security, but also in some cases to make it easier to deploy systems. So the best security is security that actually makes your life better rather than merely making your life more secure. The basic model here is to allow Kubernetes to verify the state of the system before providing access to any resources. Because we have these hashes in the TPM, because we have this channel by which we can have the TPM provide us a verifiable copy of the system state, Kubernetes can be engineered in order to call out to any system that is attempting to access a resource and ask it to provide a verifiable copy of this state. And that makes it possible for us to identify and validate the system before granting us access to these resources. So I've been working on this for the past few months, and the current model is basically a two-pronged approach. We're trying to plug this into Kubernetes at two slightly different levels. And the first is to add an authentication controller plugin. So Kubernetes has authentication controllers which are run through in a configured order and determine whether or not to grant access to the API before actually getting any lower into the stack. One of the problems we see when talking to customers is that when they're deploying bare metal to new data centers, if they don't have control of those data centers themselves, how do they get the initial secrets, the initial authentication tokens onto a system? You've basically got three approaches. You can have the system shipped to you, and you can install the secrets on it, and then you can ship the system out. And the problem with that approach is that anybody who's able to intercept the system between it leaving you with the secrets deployed, with the secrets installed, and it being racked in the data center, is able to just copy your secrets. They will be able to impersonate that system at a later date, and they may be able to gain access to your resources. So that's kind of suboptimal. The second approach is that you send the system to the data center, and then you send a person to the data center. And with luck, nobody is intercepting your technicians when you send them to the data center and extracting the keys from them. But if they do, they'll probably be able to tell you about it afterwards. So that's a much safer issue. And then person gets to the data center, racks the machine, and then installs the secrets of, say, a USB key. Problem there is that you then need to send a human to the data center. If you're trying to deploy to multiple data centers simultaneously, you're going to need to send multiple people or have one person go to a bunch of data centers, and that's going to slow down your deployment. That's going to cost additional money. Or alternatively, you can just YOLO it, ship the system, wait for it to be racked, and then just send the secrets over an untrusted communication channel and get them installed on the system. That's a bad idea. Don't do that. So our goal here was to attempt to come up with a way that allows you to deploy systems and get secrets onto them in a trustworthy way. And this is handled by, rather than just having the initial authentication be purely based on either shared secrets or TLS authentication, instead we can use the TPM. And because the TPM has this unique per-system identifier, all you need is a copy of that identifier in advance. And if you have that, either because the system manufacturer provides it to you before shipping the system, or because you had the system shipped to you and you extracted a copy of the public half of the TPM key before you ship the system out, when the system reports its state, you can then look that up against a list of trusted keys, and you can say, okay, this is a system that I trust. And you can look at its state, and you can say, not only is this the computer that I shipped, this computer is running the software that I expected it to be running. And that means that when the system comes up, you can then immediately say, okay, I trust this system, give it access to the cluster. So in an ideal world, we would just be able to do all authentication against the TPM. But there's unfortunately a problem with that, and the problem is that attestation is kind of slow. When I say kind of slow, I'm not talking about it being glacial, but we're talking about on the order of 1 second to 5 seconds, depending on the speed of your TPM. And you probably don't want every single API call to involve an additional 1 to 5 seconds of latency. That is probably incompatible with the majority of use cases. So we don't want to use TPM-based attestation in every case. Instead, once you've performed valid TPM authentication, that gives you access to the cluster, and then we can just use the secrets API in order to extract. Either we can just use the secrets API in order to obtain some shared secret that can be laid down, or alternatively, we can use TPM-based data in order to generate a certificate signing request, and we can then have an authentication certificate issued to the node. And from then on, we just use TLS for all further authentication. So that way, we get the initial validation done via the TPM, and we then get the secrets laid down in a trustworthy manner. So we only have the performance hit on the initial API call when the device is attempting to join the cluster for the first time. And that's pretty straightforward. That makes it possible for us to have systems deployed in a trustworthy manner, get the secrets onto them, and you don't have to have someone whose job it is to just walk into data centers with a USB key. That's not really a job that tends to result in a great deal of job satisfaction. So we're trying to make life better for those poor technicians. Okay, Windows has just informed me that there's an update ready to install. As long as it doesn't reboot in the middle of this, I'm fine. How do I trust that update? I don't run Windows, so I have no idea. Anyway, but there's still a problem here. If the system is compromised at some later point, it's still possible for someone to gain access to the secrets that were laid down and potentially copy those off to some other system. And that's kind of suboptimal. You would prefer, if possible, still to avoid having static secrets. And so we've gone further than this and also added an admission controller. And this means that on certain API calls, we can have another fine-grained level of TPM-based validation. So if you attempt to create a node or update a node, we can then once more verify the TPM state and ensure that the system that's attempting to access the node data is the system that we expect it to be. And this is intended to be fairly fine-grained. We can apply this to pretty much any level of the API and allow it to be configurable so that you can adopt your own policy, so that you can say, I want the TPM state to be validated on every single one of these calls, or every 5 minutes on these calls, or whatever. And that's going to be something that's going to be potentially dependent on your specific workload, your specific deployment pattern, and your specific use cases. And so this is great. It should now be impractical for someone to compromise a system in your cluster, have it join your cluster, and be able to ask for nodes to be, ask it for containers to be deployed on that node. We should now only be deploying containers on nodes that are in a verified state, that haven't been tampered with. The question is, can we go further than that? The answer, it turns out, is yes, unsurprisingly. The TPM is not restricted to use at boot time. You can perform further measurements, further cryptographic hashes into the TPM at any point during the lifetime of the system. And when the TPM hands over that state, you can also ask the TPM stack to provide a log of the updates that went into the TPM. And we've added functionality for this into Rocket in order to measure the initial state of a container. When you launch a container, we are taking the hash of the initial container file system. We're taking the configuration that was used to launch the container, and we're hashing that into the TPM and adding that to the log. So later, when you get the log, you can replay the log. You can simulate the series of measurements that went into the TPM, and you can verify that you came up with the same final value. And in that scenario, you have, if nobody's tampered with it, you then have a log file that contains a record of every single container that was launched on that particular piece of hardware during the current uptime. So at this stage, you've got a cryptographically verifiable audit trail. And that's wonderful because that means that you can, if you want, define a policy that states afterwards, if a node ever launched this container, which it turns out was backdoors and untrustworthy, don't allow this node to have any further access to the system. And we can then go and investigate the state of that system, verify that it hasn't in fact been tampered with. So we've got a proof of concept implementation of this. So Kubernetes has been an interesting project to start working with at a development level. There's a lot of code. It involves a lot of concepts that are quite enterprise, and the documentation is not always exactly as comprehensive as we'd like it to be. And Kubernetes is certainly still a project that's in development. But we have succeeded in coming up with a proof of concept implementation. And this is based around having a... the current implementation is fairly straightforward. And we have a JSON-based configuration file that simply contains a set of data about the valid TPM states. There's a couple of different ways of handling this. First of all, we just have a set of binary hashes. So for things like the kernel, you simply insert hashes of supported expected kernel versions into it. And then if the kernel hash matches that, we're good. But we try to go further than this and also support measuring the initial boot configuration. So for instance, if we're using the grub bootloader, we are measuring each line, each command that grub executes, and then providing a regular expression-based set of valid values for that, which allows you to ensure that nobody tampers with the boot configuration. So even if it launched the correct kernel, you still want to be able to make sure that someone didn't interfere with kernel parameters in a way that would potentially allow the system to be still moved into an untrusted state. But there's still a few questions surrounding this implementation. The first of them is, should this be in tree? And right now, the relevant code is all under the plugins directory, and we're interested in getting some feedback from the development community in terms of whether the ideal long-term goal here is for this kind of feature to be something that is integrated directly into Kubernetes, or something that is maintained out of tree and can then be pulled in based on specific user requirements. The other thing that's of interest is that so far everything I've described is based around bare metal deployments, which is obviously not in line with what many people are doing with Kubernetes. Many people are deploying on Amazon or Azure or the like. So far, no public cloud provider provides TPM-based functionality to their guests. I think we're expecting that to appear in Azure within the next year or so. Amazon obviously tell us absolutely nothing about their future plans. Google are potentially looking at it at some point, I believe, but we have no idea whether there's any kind of reasonable timeline around that. So we can implement certain amounts of functionality that are not quite as strong in terms of guarantee. But for instance, we could have a plugin that, rather than calling out to the TPM, instead calls out to the cloud API and queries what was booted on this instance. And once we have that information, once we make sure that the system booted the AMI, for instance, that we expect it to boot, then we could grant access based on that. That's not something that's implemented yet, but that's functionality that we're interested in adding. And it's not going to provide the same level of guarantee, and it's certainly not something that then provides the runtime functionality that I was describing. We can't have the container runtime easily measure stuff. But we are attempting to add as much of this kind of functionality to the cloud environments as possible. As vendors start providing TPM-based functionality, we'll be integrating with that as well. And obviously, we want this to be as flexible and as deployable as possible. So the current proof of concept code is sitting on GitHub. The code has been quite heavily reworked over the past week, and I haven't yet pushed that. But development is going to be taking place here certain amount of difficulty over the fact that Kubernetes turns out to be a quite rapidly developing project. And I'm certainly at this point getting quite good at rebasing over several thousand intermediate patches. I'm genuinely astonished at how quickly the project is developing. It's amazingly productive. So feel free to grab that. You're going to need some additional functionality provided at the operating system level in order to make use of this. We've got that stuff integrated into CoreOS, and we're going to be working with other distributions in order to get the same kind of functionality into their products. We don't want this to be something that's tied to our products. We want this to be something that is available across the entire ecosystem. So that's the content that I had. My expectation was that people would probably have some questions about how well this could actually be used in the real world. So I'm interested in hearing from you. Thank you.
Thanks a lot, Matthew. That's awesome. So any questions at all? I'll bring the mic over. Perfect.
Hi, I have a general question regarding TPM. So there are a couple of ports on a computer, like Thunderbird ports or a PCI port that allows direct memory access. How does TPM help against an attacker who is able to get physical access to a computer and plug in a device that allows me to modify memory during runtime of a computer?
If an attacker has physical access to your servers, you're probably in trouble already at that point. I think once your physical security has broken down, you're already in a pretty bad situation. So my initial advice would be, don't get into that situation. But practically speaking, there is hardware functionality that can be used to protect against that kind of attack. The IOMU is intended to make it impossible for even DMA-capable devices to write over memory that is being used by the operating system rather than by the specific driver for that device. So if you have hardware that supports an IOMU, which most class hardware does, and if your operating system enables that, some cases support is present in the operating system but not enabled by default, so you should check the kernel configuration, you should check the documentation, but if it's turned off, then it's a kernel command line parameter to turn it back on again. Most Linux distributions include support for it, but it's frequently, especially on distributions that support desktop class hardware, disabled by default because, ironically, despite the functionality being implemented by Intel, it very often causes problems with Intel integrated GPUs. So yeah, that's suboptimal, but you can turn it on at boot time. Intel_IOMU equals on, I think, is sufficient to enable that. And after that, it should then be impossible for someone to attack the operating system. Obviously, that doesn't help at the firmware level, but these days, firmware is also expected to turn on the IOMU. You will need to consult your vendor to determine whether your firmware actually does that.
Any more questions at all?
I'm thinking if it would be possible to make man-in-the-middle attack and just proxy all the authentication requests to valid node with valid TPM and then execute whatever you like and send fake response with correct signature?
Okay, so there's a couple of things that protect against this. And the first is that when the TPM provides the authentication data, that's signed with a key that's specific to that TPM. So as long as you have a record of the TPMs that you trust, you can make sure that the quote of the hash values is signed with one of those trusted keys. And so if someone attempts to man-the-middle you by just making up results entirely, then either the signature will be invalid or the signing key will be untrusted. So you can tell the difference between a valid response and an invalid response that way. The second attack would be to capture a valid response and then tamper and, when asked, just hand back the same valid response. And that's avoided by the machine requesting the attestation, providing a random number, and then checking that the random number is incorporated into the response. And if you hand back if you hand back a response that is correctly signed and contains a different secret, that will be dropped. If you hand back a response that's had that secret modified, then the signature will no longer validate. So this means that you can avoid replay attacks and you can avoid man-in-the-middling.
One right at the back there.
So all of this assumes that you either are using a uniform set of hardware or you're working with a vendor who's willing to help you with the management of these various hashes, right, for like the firmware and stuff. So how do you tackle the management of the various hashes that could extend all the way from the lowest layer of the stack to the top, assuming you're using commodity set of servers off the shelf?
Right, that's a great question. Now, there is, unfortunately, as I said, the fact that people have not been making much use of this technology means there's a lot of the ecosystem functionality that we would like to be present simply isn't. Vendors frequently, I have not yet found a vendor who can give me valid firmware hashes for their system. When Microsoft were defining a format for a standardized mechanism for doing firmware updates, for downloading new firmware images, the metadata associated with that does not include the firmware hashes for the TPM, unfortunately. So even in cases where people are aware of this, they still haven't really got to the point of making this easy. And so, yeah, that is management overhead. You can, when you boot a system, you can then ask it what the hashes were. So even in a heterogeneous deployment, you can still, as long as you have access to every type of system that you're deploying on, you can obtain known good values and then incorporate that into your policy. Our policy is we're not looking for single individual values. We can have an array of accepted values. So, yeah, you're correct that this is something of a management irritation, and there's currently no easy way around that. We're hoping that if there is meaningful interest in this kind of thing from the community, that vendors will start offering this kind of functionality, because if it's something that's going to make your life easier, it's potentially something that is going to be a worthwhile differentiating factor for the vendor and may drive some business. So we can try to turn this into a business-critical piece of functionality and hope that we can make people's lives easier that way.
I guess it's a call to Brandon's action there this morning in terms of like driving the roadmap, driving what's useful.
Yes, exactly.
Oh.
So to repeat something I think you said earlier, that this assumes that we're getting the machine into a trusted state at some point while it's under our control, so that we can derive these hashes and so on. How paranoid should we be in the world that we're in that that it's not coming out of the factory with something we wish it didn't?
If your hardware vendor is not trustworthy, there's really very little you can do there. If you've really annoyed the wrong people, this is not going to save you, unfortunately. There's really very little we can do against people who are able to subvert the entire manufacturing pipeline. And if we become sufficiently paranoid, then it may not even be the system vendor. If your CPU vendor has been compelled to behave against your interests, then again, this is not going to end well for you. We don't have any good way yet of verifying systems down to the individual components. I think there is going to be interest in trying to make that easier, but we're not there yet, and I don't have particularly good solutions for that problem. The aim here is really not to attempt to protect you against every single conceivable threat. The aim is to deal with the threats that we know are threats that we know are realistically likely to be deployed against individuals or companies by criminals rather than by authorities.
So then follow-on question. On the face of it, I can't see any other ways in which this doesn't work, right? That it seems like this gives us the trusted chain all the way up. Are there other realistic exploit vectors that this doesn't address?
So this verifies the initial boot state. Now, one thing that it does not do at the moment is verify the runtime state of the overall system. It's not able to measure the contents of memory once the system is running. Even if it could, figuring out what a valid state there is so far an unsolved problem. There's a lot of active research being done in this field, but we're still at the point where we can only really validate up to about 95% of system state at best, and that's in carefully constructed academic environments. If someone compromises the system at runtime, this is not going to protect you. The aim is to make sure that if someone does compromise the system at runtime, they're not able to do so in a persistent way. They're not able to do so such that when you reboot the system, it will come up in a still compromised state. If you perform a security update and reboot, you should then be able to verify that you've booted into the updated system and know that you don't have any known security holes. There are certain things we can do to make runtime, certain kinds of runtime attack more difficult. There's interest in using hypervisor-based technology to perform introspection of the system and validate certain aspects of the runtime state, but we're not yet at the point where that's deployable.
So the main thing that this offers then is that we can tell what was present during the current uptime.
This tells you which containers were launched and the state they were launched in. It doesn't tell you what the state of the containers is at present.
Time for one final question, if there is one. Yep, cool.
This is pretty simple. Do you have documentation or a write-up on how you would use this? Because it's not on the GitHub repo.
Right. So documentation is on my list of things to do. Okay. The main thing is
after you complained about the Kubernetes documentation.
Yeah, I know. Complain is not really the right word there. I think when things are in a state of constant churn, documentation inevitably falls by the wayside. I'm as guilty of that as anybody else here. So my intent is, now that I think that I've got the on-disk configuration formats nailed down, my aim is to now document what deploying this looks like, which tooling you need to do that. I will try my best to get that done on my flights back, and then it will be in the repo there.
Cool, thank you very much. I think under subtle plug, CoreOS are hiring by the look of it.
Yes, we are in fact hiring. Hooray.
Cool.
So if you'd like to work on this or anything else, let us know. I'm going to be around for the rest of the day, so if anybody does have any additional questions, feel free to come and find me. I'll probably be around the CoreOS booth.
Thank you once again.